Everybody say hi.
Hello. Hi.
I don't know. I did it the last time. Okay, so one of the things I worry about is saying the same thing over and over again. And I'm going to say the same thing right now because we'll summarize really fast. And that, oh God, all right. Doing this off camera, you see. Anybody watch the television series Longmire? Anybody ever heard of Longmire?
Heard of it, but I've never seen it.
This is one of the shirts that is worn on the television series Longmire. It's one of my all-time favorite television series. But forget that. God, this is actually live now. We're going to post this to YouTube. Great. Okay. Where's my good side? Stop it. Now. Oh, geez. And then this thing is beaming and, you know, because Robertson and I think, are two of the faculty that hate PowerPoint the most. And I use figures some, but I like having the board. All right. So what we're doing is getting at the very basics. We are starting from the very bottom here because some of these issues about bonds become a really critical point when we start talking about the macromolecules and how they interact. So the last thing we were talking about was the atomic nucleus and the fact that we have protons, neutrons, and electrons. And that's as far down as I ever go. You have quarks and bosons and things, but no, please. One of the things I always think about, this is what we were talking about on Wednesday, is the amount of space that there is in the atomic nucleus is really quite vast. And there really is nothing there. I mean, we should be able to walk through walls and things, but, of course, at least not yet, can we do that? One of the little points we made was the proton number. This is determining the element's identity. The neutron number, if it doesn't match, we have an isotope, at least that's my better definition. I think the chemist folks might say that the most common form of the element in the Earth's crust or on the planet is the element, and then other things are going to be isotopes, because that gets me into trouble when I start talking about hydrogen isotopes, in that the most common form of hydrogen on the planet is, in fact, just a single naked proton. So the isotope is considered one proton, one neutron, and that is what we call deuterium, and one proton and two neutrons is tritium. We'll talk a little bit about radioactive isotopes and things occasionally in here, because there are certainly some experiments done back, 50s and 60s that did use radioactive isotopes for some really critical information, but not so much. Electrons are a very important part of this. Obviously, we have, because from your chemistry, we have the different orbital shells, and it's the number of electrons in the outermost shell that is going to determine whether the molecule is reactive or not and what kind of bonds it forms. All right, all one good. The first step, though, in terms of really getting into some of these ideas of macromolecules, is determining the idea of bond strength. So we start out with the strongest bond we can generate is, of course, the covalent bond. And we define this as an equal sharing of electrons. All right, so we have to get two atoms pretty close together in order to make a covalent bond. And I kind of think of it like this, where we've got an atomic nucleus with the protons and neutrons and whatever here, and then we've got the electron orbiting around. And then here is the other with the electron orbiting around. Okay. Now, we know like charges are going to actually generate some opposition forces, and what we're going to have to do is overcome that and get these guys close enough that the electrons can be playing tag and zooming around, chasing each other. So if we think about our analogy of the domed stadium, where we have this sphere, actually, and we're going to make a covalent bond. Think about having one sphere here and one sphere in Bloomington. And we're going to have some kind of magic force. I think of it as leashing up several 100,000 dachshunds and just start lashing them. And they start pulling these two atoms together. They start getting closer and closer. And there's going to come a point somewhere probably around Varroa and Wapella where the electron forces are actually pushing them apart. And so you have to really urge those dachshunds on. Come on. And then finally they get close enough that they break through this Coulomb barrier, and all of a sudden, pow, you make the covalent bond. So it takes energy to overcome that repulsive force to get the electrons close enough that they actually are now orbiting the two different atomic nuclei. And one of the truisms of this whole biz is the amount of energy that it takes to build a bond is going to be equivalent to the amount of energy it takes to break the bond. And so consequently, covalent bonds being our strongest bond, they require a fair amount of energy to break them apart. Now, just from a sort of a tactile perspective, we're working with carbon molecules here pretty much in biochemistry, Molec and Cell biology. And so we can think of how carbon-based materials operate and behave. And as I say, I teach the non-majors class in the biochemistry of food. And so I've been a baker and cooking creative person for a very long time. I often think about the biochemistry when I'm cooking stuff. And one of the truisms is going to be that covalent bonds in organic molecules, like what we've got here, are going to be pretty stable up to about 450 degrees. Meaning that, yeah, stuff will decompose and it'll begin to denature, but you're not going to break bonds unless you put a lot of heat into it. So in terms of, charring and burning stuff, that is breaking covalent bonds. And if we think about the energy it takes to get that going, it's pretty high. So covalent bonds are very, very tough. Now, this is not for everybody, but in general, certainly carbon-carbon covalent bonds, in order to break them, you got to set them on fire. So that is our number one tough bond. 450 degrees, what is that in Celsius? I have no clue. And I only know this because of the book Fahrenheit 451, which is the temperature supposedly to catch paper on fire. Paper represents every kind of carbon-carbon molecule I can think of, so there you go. I would tell you, though, that proteins, fats, everybody, you're going to have to get them to 450 or higher in order to break them apart. Tough, tough bonds. Now, number two, and actually it's a distant number two, is the ionic bond. And the ionic bond is essentially an unequal share of electrons. So that means that we have to have two ions. And a classic example of this would be sodium, which is missing an electron compared to its proton number, and so it carries a positive charge. And chlorine, which has got an extra electron compared to its number of protons, and so it's carrying a net negative charge. And with these guys, we have, because we have opposite charges, we have less energy required to bring them together. And the proton, or the sodium atom, is desperately seeking an electron to sit and cuddle and pet. And the chloride has got one electron too many. Get the heck out of here. And so these guys get together, and ba-da-boom, we've got an ionic bond. Now, ionic bonds can form fairly easily, and they also can break apart quite easily. Particularly, this number two weakness has to do with them being in the aqueous environment. It's just another little thought that has popped in my head as I'm thinking about this, and I had to go pursue a chemist, one of the guys upstairs on the fourth floor, to ask him, why is this? Why do we say ionic bonds are weaker than covalent bonds, given that in order to break salt apart, you have to heat it to like, 1,500 degrees. I mean, there's a form of pottery called raku pottery where you have like raw natural gas blowing into your ceramics. Have you guys done ceramics? And you take a handful of rock salt and you throw it in there. And you don't want to be too close because when it breaks apart, it liberates chlorine gas, which would be bad to breathe. And you get all these really cool streaks and things coming out. So, it's like salt. Man, that takes a ton of energy to break it apart. How is it that we say it's a weaker bond? The answer is biochemistry is all about the chemistry of molecules in water. In a non-aqueous or a dry environment, an ionic bond is way tougher than a covalent bond. But in an aqueous environment, which is what biochemistry is all about, it is weaker. One little, just an abstract point. I think it is February 15th. Perseverance is landing on Mars. Do you know of this? Are you excited about this? Are you have this on your calendar to watch? No. Perseverance is the latest Mars rover, and it's landing in a spot that looks like it could have been a lake bed at one point. The search for life outside of our planet is pretty much based on the search for water. That we could have some sort of weird-ass life floating in the clouds of Jupiter, but I suspect it might be so different that we wouldn't recognize it as life. But stuff that is in water, that is something we're going to be able to see. And I'm really hoping that there's going to come a point in Molec and Cell where we can start the day off or the semester off by saying, now that we have discovered life on a different planet, what kind of things can we compare? And just saying right now, when we do discover life on a different planet, it's probably going to be using phosphate as an energy carrier. There are so many things that are fundamental to life on our planet that if we're going to find life outside of our planet, it's going to have a lot of similarities. Just a little minor point. So water is key to doing any kind of biochemistry. And that brings us to our third bond. And arguably, yes, my favorite bond. And that is a critical thing. It's an interaction, not a bond, but regardless, it is known as the hydrogen bond. Not to be confused with the hydrogen bomb, but a hydrogen bond now only occurs under very specific circumstances in which we have an electronegative atom. And not all atoms are electronegative, but oxygen most definitely is. Meaning that it tends to hold the electrons and pull electrons towards it. And so when we set up a molecule, and it's very easily seen in a molecule of water, but one of the things I always say, whenever you see OH, always think, the possibility of hydrogen bonds. When we have water, because oxygen is so electronegative, it starts to hold the electrons around it, and only rarely do they come out to the hinterlands of hydrogen. And consequently, we have a slight charge in that we have a little negative charge up here and a positive charge here. So the hydrogens have a slight positive charge, the oxygens have a slight negative charge, and with a single molecule of water, it's a very small amount of water, nothing really is interesting happening, but when we start adding water molecules, we get this charge interaction, and we can begin making a mesh network or a mesh network of these electrostatic charge interactions going on here between the oxygen and the hydrogen. And this hydrogen bond is a delightful sort of sticky Velcro-like thing. And it's one of the things I think about whenever you've got a molecule, a substance, stuff, that is not an oil, like a fat. This didn't work. But if you've got something that it's thin when it heats up and then thickens when it cools, and if I was to ask you, think of something that does that, and you would say, what about Jell-O? And I'd say, exactly. Or various kinds of gravies. This is an example of hydrogen bonds. Anything that you can break apart by heating it, and then it will congeal when it cools, is a hydrogen bond. And so just as an example, if you take all kinds of adhesives and you heat them up, they almost like duct tape. It will become really gooey and loose. And that's because lots of adhesives are based on hydrogen bonding going on. All right, so the hydrogen bond is critical. And one of the really important things it does is it makes water behave in a really bizarre fashion. And one of the ways that we can see just how strange water is, and I'm trying to remember bringing some of my little solutions. We can do it like a demo of looking at water droplets. If we were to erase that, because I need more room on the board. I don't know, that's probably bad. I may change colors here, though. Let's see. If you were to compare hydrogen sulfide, which is H2S, with water, which is H2O, we see the power of the hydrogen bond. And that hydrogen sulfide has a boiling point of something like minus 250 degrees centigrade. And I just pulled that number out of the damn air. All I know is it is so cold, there is no place on the planet that hydrogen sulfide is going to be found in a liquid form. It's always a gas. Now, what is the boiling point of water? It is, of course, 100 degrees centigrade, 212 Fahrenheit. So water boils at a much higher temperature. Consequently, liquid water is pretty darn common here on the planet. And in fact, there is no place on the planet, generally, outside of like a volcano or whatever, that is so hot that water is going to be in a gaseous form. This is a critical thing because water provides this sweet spot of being liquid at a temperature such that there's enough thermodynamic energy that we can actually carry out biochemical reactions. So you can get hydrogen sulfide, H2S, to be liquid, but at that temperature, there is so little thermodynamic energy, you just can't get biochemical reactions to happen. So the fact that hydrogen bonds can form in water is critical to life on our planet. And we're going to invoke hydrogen bonds a lot in terms of structure and things. And another thing to keep in mind with hydrogen bonds is while water boils at 100 degrees centigrade, and that means you're breaking those hydrogen bonds, what I can tell you is that in most biochemistry, biochemical polymers, we're going to break hydrogen bonds probably somewhere 120 degrees. There may be a few hydrogen bonds that can handle up to 140 degrees, but above 140 degrees, forget about it. Now, again, I'm just making this up, so don't tell. It's one of the things I really do worry about having this actually recorded, because people can come back and say, you said this and that wasn't right. Because if it's not recorded, they're like, oh, I didn't say that. Yes, you did. Here it is. Like, oh shit, sorry. Like, just then. I'll be heavily editing these tapes. All right, so what this means is hydrogen bonds break really easily. When you're running a fever, you can pull, you might be able to pull 105 on your own if you were to subject somebody to the desert and no water. Your body temperature can go up to 110, which is lethal. But on a fever, you might be able to do 102, 103, maybe 104. And what you're doing is that little difference in temperature is actually beginning to break hydrogen bonds. And that's part of what happens when you run a fever. Anybody ever heard of sous vide cooking? No one. It is a style of cooking where you use a thermal hot water bath, like an immersion heater and a circulating bath, and you put your food into like a Ziploc bag, suck all the air out of it, stick it into this bath, and you run the temperature at about 120 degrees, which is warmer than a bath water, but it's not so warm that you can't nicely put your hands into it. I mean, it's pretty darn comfortable. No, 110 is comfortable. You can put your hands in it. You won't scream when you put your hands into it. And so it's not that hot. But if you get the internal temperature of a piece of meat up to 120 degrees, it's cooked. You denature all the proteins there. So it is an interesting way of very gently cooking things. And that's what we'll see as we start talking about macromolecules. The idea of cooking really comes down to mostly breaking hydrogen bonds. If, when you're cooking, you're breaking covalent bonds, you're setting stuff on fire, which, that's okay, but, a nice char on your steak or something. All right, so those are our bonds. One last little story bit. Now, when we take salt and throw it into water, it dissolves, yes? Yes. In addition to going into solution, we're breaking the ionic bond. Now, when we take sugar and throw that into water and dissolve it, it's going into solution, but the covalent bond isn't breaking. And that's actually a really critical thing to think about, in that we can get lots of stuff to dissolve in water, but it's not dissociating or not breaking the bonds. And we can tell this by the ability of these solutions to carry an electrical current. So what you can do is grab your roommate and say we're going to do an experiment where you're going to take an extension cord and cut the female end off, the end that you're going to plug into. Plug it into the wall, but before you do that, strip off about that much of the insulation on the two ends, and now plug it in. And then get yourself a bucket of water and put the two ends in there and step into it. Now, you want to make sure that it's really pure water, because very, very pure water actually is a pretty good insulator. It's got a high resistance level. You want to make sure you wash your feet off real well so there's no salt in your feet. But you stand there with that electrical current in there, and you're just happy as you can be. And then you can take a bag of sugar and dump it in there. Stir it up, and you're fine. There is no charges there to transfer the electrical current. Now you step out, and you have your roommate step in and say, see, you saw me. Now look, let's go ahead and put this salt in and see what that does. You put that in, and you wouldn't really want to do that. But what this is indicating is we can tell if things are ionizing by their ability to carry an electrical charge. So stuff will dissolve, but that's not breaking covalent bonds. Stuff will dissociate, and that will break ionic bonds, but really the only way you can tell is to see if it'll carry an electrical charge. And hydrogen bonds, we break them by adding a little bit of heat, and we're now ready to start getting into some of our macromolecules. All right, on that point, it's Friday, the weekend. Is it any different than any other day of the week now? I don't know. I'm going to stop this, and I'm going to say very important things after I stop it that the Monday and Wednesday people will miss.